Hello everybody, and it's back to physics, and more specifically it's back to causal fermion systems. Or rather I should say, this is the first video I've ever done on causal fermion systems, so this is the introductory video on causal fermion systems and how causal fermion systems relate to my theory of quantum gravity, if they relate to my theory of quantum gravity at all. So I'm just looking at the Wikipedia page now for causal fermion systems, and I know one should never use Wikipedia, but it is rather convenient, and it's a little more convenient than actually going into Felix Finster's research on causal fermion systems, or his papers, which I have read also. But yeah, so here we go. I'll just do the introductory paragraph and a few more bits from the Wikipedia page. The theory of causal fermion systems is an approach to describe fundamental physics. It provides a unification of the weak, the strong, and the electromagnetic forces with gravity at the level of classical field theory. Moreover, it gives quantum mechanics as a limiting case and has revealed close connections to quantum field theory, therefore is a candidate for unified physical theory. Instead of introducing physical objects on a pre-existing space-time manifold, the general concept is to derive space-time, as well as all of the objects therein, as secondary objects from the structures of an underlying causal fermion system. This concept also makes it possible to generalize notions of differential geometry to the non-smooth setting. In particular, one can describe situations when space-time no longer has a manifold structure at the microscopic scale, like a space-time lattice or other discrete or continuous structures on the Planck scale. As a result, the theory of causal fermion systems is proposal for quantum geometry and approach to quantum gravity. Causal fermion systems were introduced by Felix Finster and collaborators. Felix Finster is the great German mathematician who came up with this rather beautiful and austere notion, and also rather, I think, essentially or quintessentially mathematical notion, more than anything else, and possibly a little unphysical, if you see what I mean. Not to say that this is a bad attempt at all, and that this is very possibly very close to the idea that I've been developing over the last few years, and this is why it interests me in particular, this stuff. So, in particular, one can describe situations when space-time no longer has a manifold structure on the microscopic scale, like a space-time lattice or other discrete or continuous structures on the Planck scale. So, this is something that, so what he's really describing there is something like an Antisitter Space, which is a space-time, as I understand it at least, without a manifold structure. And when he's talking about lack of space-time lattices or lack of other discrete or continuous structures on the Planck scale, I think that that's a little bit misguided, since I still suspect that space-time does have a structure, and that structure is formed out of electric negative, yes, fermions, electrons, appearing and disappearing for incredibly short amounts of time, i.e. Planck times, and exchanging W plus and minus particles, W plus and minus vector or / gauge particles with protons, or quarks I should say, or bundles of quarks, i.e. protons, and that gives rise to gravitation and the phenomena of particle masses. So there are a number of very interesting things about causal fermion systems, or perhaps there's nothing interesting about them at all, and that this is a totally wrong idea. I actually have no idea. I really don't understand causal fermion systems. I think that's the problem here. And it could also be a case, and this is something that Wolfgang Pauli always used to say, this could be a case of something being not even wrong, if you know what I mean. And I think this may be the case actually with all quantum gravity theories, that they might, all of them, not even be wrong, which is bizarre, isn't it? Since there's about 8 or 9 major conflicting theories of quantum gravity, of which causal fermion systems is one, of which string theory is one, of which loop quantum gravity is one, of which Euclidean quantum gravity, Stephen Hawking's brainchild, is another one. And they might, in a sense, all be correct. In a sense, they might all be wrong. Oh, they might not even be wrong. Yeah, they might not be wrong at all. And that might be the most irritating thing about them. And it goes on to say things like, the above constructions be carried out in more general spacetimes, more over the taking of abstract definition as the starting point. Causal fermion systems allow the description of generalized quantum spacetimes. The physical picture is that one causal fermion system describes a space-time together with all structures and objects therein, like the causal and metric structures, wave functions and quantum fields. In order to single out the physically admissible causal fermion systems, one must formulate physical equations. In analogy to Lagrangian formulation of classical field theory, the physical equations for causal fermion systems are formulated via a variational principle, the so-called causal action principle. So it's introducing yet more and more ideas. Since one works with different basic objects, the causal action principle has a novel mathematical structure where one minimises a positive action under variation of a universal measure. The connection to conventional physical equations is obtained in a certain limiting case, the continuum limit, in which the interaction can be described effectively by gauge fields coupled to particles and antiparticles, whereas the Dirac sea is no longer apparent. So, yeah, you get stuff like this, and it revivifies this idea of the Dirac sea, which is what worried me in particular, since Dirac seas are formed of electrons, and causal fermion systems describes these interacting fields of electrons, and I was really hoping on a level that it would be the same idea as mine. However, I'm just not certain it is, because it's not clear enough. It doesn't come out and clearly state anything like gravitational fields are composed of electrons, which is really, it sort of alludes to that a little bit, but nothing here is certain. Nothing here states explicitly that gravitational fields are composed of electrons, which is what I'm really looking for. And yeah, that's really the heart of all this. Like, what I think causal fermion systems are really is just like a sort of a new mathematical language in which to describe fundamental physics, and you can come up with those to your heart's content, I think, more than likely, rather than this being anything like a physics theory. It might be mathematical physics. It might be a sort of a much more abstracted, mathematized notion to allow for a unified physical or a unified mathematical framework within which you can describe physics, rather than it saying anything explicitly about the universe and how it operates. And crucially, what it's trying to do, I think, is reveal close connections with quantum field theory, yes. But what I think it's trying to do is trying to upstage quantum field theory and the mathematical languages used therein, and just by providing a new mathematical language. And it's like, well, that's a very interesting thing to have done. However, it doesn't tell us anything about the universe, not really. I think it's, and also this isn't falsifiable for that reason. So it's not really a theory of physics, since it doesn't make any testable predictions so far as I'm aware. And yeah, this is just mathematics. This is just a new way of describing nature or describing fundamental physics in a mathematical sense, but without creating theory. So it's not really theoretical physics, it's more like mathematical physics. What I want from a theory, really, is a theory, I suppose, because it's supported by evidence more than likely. But it's not a hypothesis, I should have said. What I want from a hypothesis is for it to state something, for it to be testable, basically. For it to make a statement about the universe that can be tested. And also, I'm not so taken with this idea that objects on the space-time are secondary to an underlying causal fermion system. I think if you can have a causal fermion system, the underlying thing is that, the fermions themselves, those are the primary objects in the universe. And I suppose space-time and the objects therein may be secondary. to the fermions themselves. But really the space-time is made of fermions. That's what I'm trying to get at. So just to diagrammatise quickly, and this is the same logo as the logo on my channel, you know, this circle with the dots around it. And people have said, is this an atom, or what is it? It could be an atom, I think, possibly. It could be a planet, it could be a star, it could be anything. And so what this is, you could say that this is something like a Dirac sea coupled to a massive object, or you could say that it's a gravitational field. And I'm just trying to establish that there's a parsimony here between that sort of idea and this general relativity idea of the ball on the sheet, you know, with the curvature in space-time around it. And I would say, like, general relativity, yes, fine. However, we just need this quantum upgrade, like Richard Feynman said, to general relativity, and invoke the notion that the discrete points of space-time are electrons. And therefore you have the unification between gravity and electromagnetism. And from that you can build in unifications between the strong and the weak interactions. But those fall out quite elegantly and organically from that mode of thinking and from that way of thinking. And I think whatever the case is, whether or not Felix Finster has come up with the same theory that I've come up with, ultimately the idea will be that space-time is formed of electrons, that gravitational fields are electron clouds, or electron densities, or whatever you want to call them, and that generates mass, and so on and so forth, in the classical sense of gravity giving mass to objects, and not the quantum field theory sense of Higgs fields giving mass to objects. So, causal fermion systems, very, very interesting stuff. Very, very, fascinating attempt and a fascinating approach to all this. But it seems as though, I just get the sense that whenever Felix Finster's trying to explain something, he just bolts in a new physical concept like a Dirac sea, which is a bit of an antiquated concept really used to describe antimatter back in the day before it was upstaged by something else. I can't remember what it was upstaged by right now. Actually, I can go to the Wikipedia page and find out. So the Dirac sea is a theoretical model of the vacuum as an infinite sea of particles with negative energy. It was first postulated by the British physicist Paul Dirac to explain anomalous negative energy quantum states predicted by the Dirac equation for relativistic electrons. Electrons traveling. Maybe I've misunderstood the Dirac sea, actually. Maybe, yeah. I thought it was negative charge, not negative energy. No, I don't believe that any particles have negative energy. That would imply that they have negative masses. No, that's not possible. Yeah. Maybe the Dirac sea was disposed of rightly for very good reasons, that it's unphysical, and that hence causal fermion systems are unphysical, which is a bit of a weight off my mind, because I was hoping that, frankly, it would be, that I'd be right. Inelegance of Dirac sea. Despite its success, the idea of Dirac sea tends not to strike people as a very elegant. No, not really. The existence of the sea implies an infinite negative electric charge filling all of space. In order to make any sense out of this, one must assume that the bare vacuum must have an infinite positive charge density, which is exactly cancelled by the Dirac sea. Since the absolute energy density is unobservable with the cosmological constant aside, the infinite energy density of the vacuum does not represent a problem. Only changes in the energy density are observable. No, it doesn't. You don't need that, really, if you can have a Dirac sea. infinite negative electric charge, which is what I initially thought a Dirac sea was, a sea filled with electrons, space being filled with electrons, or with negative charge, right? However, what we also know about electrons is that they absorb and emit photons, and that space is also filled with photons. So this note on the inelegance of the Dirac sea is, one must assume that the bare vacuum must have an infinite positive charge density, which is exactly cancelled by the Dirac sea. No, you don't have to assume that at all. You don't have to assume that there's an infinite positive charge density, which is exactly cancelled by the Dirac sea at all. You can just have all of these negative energy particles spaced out by photons, and photons form part of the underlying structure of space, which I think is a very rather elegant idea and adds elegance into the idea. However, you could also assert and state that yes, we also have some evidence possibly of the infinite positive charge density, in that we know that positively charged particles exist and that they seem to be fairly exactly cancelling the negative charge density of the universe. So, for example, we know that at the beginning of the universe, X number of electrons were emitted along with X number of up quarks, down quarks, and so on. And that, yeah, these did seem to line up pretty much exactly and create atoms. And or lead to nucleosynthesis, and that nothing was left over, which is bizarre. It's very, very odd that that's the case. It's very, very odd that there's no sort of leftover remainder or lump of electrons or protons gurgling around in the universe somewhere, and that all protons seem to have associated electrons, since they usually come in the form of atoms. Nonetheless, that is how it happened. So, yeah. I should really do more reading on this before I do a video about it. Revival in theory of causal fermion systems. Dirac's original concept of a sea of particles revived in theory of causal fermion systems, a recent proposal for unified physical theory. In this approach, the problem of the infinite vacuum energy and infinite charge density of the Dirac sea disappear because these divergences drop out of the physical equations formulated by the causal action principle. These equations do not require pre-existing space-time, making it possible to realise the concept that space-time and all structures therein arise as a result of the collective interaction of the sea states with each other and with the additional particles and holes in the sea. Still, this stuff, the causal action principle, it doesn't really tell me anything. And sea states, collective interaction of sea states with each other and the additional particles and holes in the sea, it doesn't really tell me anything either. Well, nothing that I don't already know. It doesn't make explicit what's going on there physically. That's its only problem, possibly. It doesn't say, electrons interacting with other particles or exchanging bosons with other particles leads to gravity. It doesn't say that. Or leads to them acquiring mass, which is a problem. So that's my conclusion. I'm sorry, it's going to be a very unsatisfying conclusion to a video about causal fermion systems, is that I don't know what it's trying to say. I don't know what to say about it. Is it just a mathematical framework? Is it a physical theory? I'm not certain it is one. Is it making testable predictions? Negative energy, no, most certainly I don't think so. Negative energy is a concept used in physics to explain the nature of certain fields, including the gravitational field and various other quantum field effects. I don't believe that there's any such thing as negative energy. I think that would require negative mass. So I'm just looking at different articles wherein the Dirac notion is described in different ways to try and make more sense of it. According to the theory of the Dirac developed by Paul Dirac in 1930, the vacuum of space is full of negative energy. The theory was developed to explain the anomaly of negative energy quantum states predicted by the Dirac equation. The Dirac theory correctly predicted the existence of antimatter 2 years prior to the discovery of the positron in 1932 by Carl Anderson. However, the Dirac theory treats antimatter as a whole, where there is the absence of a particle rather than as a real particle. Quantum field theory developed in the 1930s deals with antimatter in a way that treats antimatter as made of real particles rather than the absence of particles, and treats a vacuum as being empty of particles rather than full of negative energy particles like in the Dirac theory. Quantum field theory has displaced Dirac theory as a more popular explanation of these aspects of physics. Both the Dirac and quantum field theory are equivalent by means of the Bogoliubov transformation, so the Dirac can be viewed as an alternative formulation of quantum field theory and is thus consistent with it. Yeah, okay, sure. Yeah. This is very, very tricky stuff to try and understand, to try and glean understanding from all this stuff. However, yeah, I don't think the Dirac is entirely correct, and I do think a new theory is necessary, one that treats the electrons as being bound to objects within the universe, that rotate in tandem with those objects and that give rise to forces of resistance with other clouds of bound state electrons, and that these comprise space-time. I'll have to do another video explaining my theory of quantum gravity more effectively, I think. Or I'll try to, or maybe even a documentary, who knows. And yeah, thank you everyone for watching. It's been my video on causal fermion systems. Sorry it's not been very satisfying, I haven't come to any conclusions about them, but I will try to do so in the future. So thank you very much for watching, bye bye bye, love you lots.